The latency of an instruction is the number of clock cycles it takes for it to produce a result. And the latency is not affected by pipelining, since the instruction still needs to perform each task that it has to do. But the throughput, which means the number of produced results per clock cycle, that can be improved. Okay, but we should also know that not all instructions are pipelined. For instance, divide. And the reason is that they are too rare and too complicated to pipeline. What can we do to improve the performance of a processor beyond pipelining? Next week we will start with cache memories, but which are essential. But another way to increase the performance is to not start one instruction every clock cycle, but to start several instructions every clock cycle. Okay? To have any use for that, we need to have multiple so-called functional units. In this pipeline here, this is called, the hardware which can perform an add, that's a functional unit. And a superscalar processor can have maybe, it differs, such as 10 functional units. Maybe 2 for load, 2 or 3 integer arithmetic, and similar for floating point arithmetic, for branch, and for various other things that it can do. So what it can do then is to take in the decode groups of instructions and send individual instructions in a group to different queues. There is one queue for each functional unit. So what this means is that instructions will execute not necessarily in the same order that the compiler put them in the program, but the order of their execution depends on the queue length for the different functional units. Okay, so how can this work? Clearly, we must take care of data dependencies, otherwise nothing could be correct from this. And what's also important is that the processor guesses where to fetch instructions. And why is that? Well, as we saw in the previous video, when there is a branch and the processor fetches the wrong instructions, then they will be wasted. So then the question is, how frequent are branch instructions? Actually, they are very frequent. Well, it depends on the code. If we have a huge loop with numerical, lots of floating point operations, then maybe it could be one branch per 100 instructions. But for a normal code, there is no such thing as a normal code. The code that is normal, it's the one that you execute. That's what you think is normal, and the same for everyone else. But frequently there is one branch, at least one branch per such group. So there can be one branch every 5 instructions, for instance. But obviously it depends on the kind of program. Okay, and that means it would have to waste clock cycles since after every group has started executing without branch prediction. So branch prediction is absolutely essential. And what it does then is to guess it will need instructions from a certain address and just fetches them and starts executing them without knowing that they really should be executed. That will be determined later. Okay? So branch prediction as a concept is trivial to understand. It just guesses where to fetch instructions next. And what it enables is, well, not only that, the other two features here are required as well, is speculative execution. It's speculative in the sense that we don't know whether it should be executed. And in case we guess wrongly, we need some way to undo what we had. And for that, we need to understand the exact order that the program contains the instruction. I mean, the program order, that's the sequence of instructions that the compiler has produced. And that's the real order that the CPU must preserve. And for that, we have something called a reorder buffer. So this is simply a first in, first out queue, so that if we decide, say it looks like this. I will come to that more in detail, but say we have some instruction here, a plus, and the older instructions are there, and the newer instructions enter the queue from here. Okay, and maybe here is a branch, and here is a minus, and here is a multiply. Okay, so what this reorder buffer does is it keeps track of the program order of each instruction. So they enter here and leave there. And if this branch concludes that it guessed wrong, then all instructions after it in this queue are thrown away. Okay, then we need something called register renaming as well. And I will come to that shortly. So, the processor guesses where to branch. And to do that, it uses statistics that it collects during the execution of the program. So it has tables which says this branch is likely to take or to jump or to not jump. And then it will fetch all these guessed instructions. Okay, not much to explain. But register renaming, when we have speculative execution, we still don't know where to, if these instructions should be executed. And if we would modify the real registers and then realize afterwards that this instruction should not have been executed, then we are in bad shape. So what we do instead is to create something called rename registers. And in the register file, say we have the register file, and for each register from R0 to R31, then we also have another field which says which so-called rename register is containing the most recent write to this register. We will now see what happens. Say we have, I write it like this. R0 is assigned, we can say R1 plus 2. What happens then? Okay. well, this then we have the reorder buffer. So the plus is now the first instruction. Okay, and when it fetches R1, it looks here. Is this R1 located in the register file or in such a rename register? How many rename registers can there be? Well, for instance, if we have 32 integer registers, we can have 80, that's just an example, rename registers for integers. Okay, so we check this field and it's empty, as we can see. I mean there. So what this instruction does is to read the value of R1, which is here. Okay, so it has decoded and fetched the operand. Now but when it sees that it should write to R0, it will request a new rename register. Okay, that means here we write Rn, for instance, say number 1. Okay, then we can have another instruction. And what this means is that this instruction will write the value, I mean the sum here, into this register. So, okay, so we have this array and with normal 64 bits plus another field which says which rename register is used. Then we have the data for the rename registers. So this can be Rn0 down to Rn79 if we have 80 of them. Okay, then we say there is another instruction, and just to make it more interesting, we will also write to register 0. And we can say that it should read R0 and subtract 5, for instance. Okay, so what does the processor do now? Well, it says it should fetch register 0. Okay, let's see where is register 0. It checks if it is being calculated into rename register, some rename register. Okay, it is. So this subtract cannot execute until rename register 1 has got the value. Okay, and what else happens? Well, it should also get a new rename register for itself to write its value in. Okay, so now let's say it this one will have rename register 1, and we can say this one writes to rename register 4, because that's easier to draw here. So okay, it could be any of these 80 except R0, because that's already, I mean rename register 1, because that's already in use. Okay, and then we can say there is another instruction, R1 equals, well, R0 times, well, we can take R1, for instance. Okay, so what should this one do? It should read register 0. It checks where is registers the value of register 0. It's being computed into rename register 4. Okay, so it knows it cannot perform the multiplication yet. It has to wait until this has a value. And also it should read register 1. Register 1 is available in the register file. It knows that since there is no rename register noted here. Okay, and then so it can fetch that operand, and then it should get a new unused rename register for this. So let's say it uses rename register, well, 3 for instance. Okay, so now rename register 3 is noted here. I forgot to put this in the reorder buffer and then the multiply. Okay, so you can see a system that when the Superscalar processor wants a register, it checks here and takes the it's like a ticket to get the most recent version of that register. Okay. Previously, these two instructions, they have an output dependence, since both want to modify register 0. But this one does not have to wait for that one to write register 0 to the register file. It just notes that it can write its value to another rename register. Of course, it has to wait since it actually needs register 0, but that's a different issue. Okay? And what can we have as use for this? Well, there are 2 uses. First, anti and output dependencies. They can be ignored. I mean, they don't reduce performance. And secondly, we can have speculative execution, since if we can modify this reorder buffer. Say we have a branch here, branch conditional, okay, and then we realize that this branch was false. I mean, it mispredicted. What we do then is to remove everything that's here. So all these instructions are just forgotten. And the nice thing is that the real value of the registers, they have not been destroyed. Okay, so when is suppose that there was not the branch there. Suppose it looks like this instead. Well, when this instruction has computed the value, and it is also the oldest instruction in the reorder buffer, then there is absolutely no risk that the processor can regret starting this instruction. It will certainly finish it, and it should be finished. And the sum of R1 and 2 should be written into this register. That means the oldest instruction can copy its value into the real register. So, well, there is some value. And then that one leaves the reorder buffer. And usually there are several instructions, one at a time, leaving each clock cycle leaving the reorder buffer. But the important thing is it's only the oldest instructions that are allowed to update the register file. So, as one student some years ago remarked about this system, it is that someone has made some good thoughts about how to produce an efficient system. So this is really nice. And in lab 5 you will see how this works. Not that the reorder buffer is visible, but you will notice that there are rename registers. Okay, what happens when all the rename registers are in use? Say we have 80 instructions in the pipeline, and they all use integer registers. I mean, write to integer registers. Then there comes another register instruction, and it also wants to modify an integer register. Okay, then there are no rename register left, so it has simply to wait until there is one. Therefore, the number of rename registers for the hardware designer should be sufficiently high so that this is unlikely to happen. But on the other hand, there should not be so many rename registers that it cannot happen, because then it's usually waste of hardware resources. So it's a very, very complex trade-off to make a good processor. Okay, so that was most of what is needed to understand how modern processors work with these three: branch prediction, fetch instructions from the guest address, put all instructions in order into this reorder buffer so that we can know which ones to throw away and which one is the oldest still in the pipeline, so that one is allowed to update the read registers. And rename registers, temporary registers that can tell a later instruction where to look for the data. Okay, so when one instruction has updated its rename register, the pipeline will distribute the value to the instructions that are waiting for it. Okay, so this is basically what I have already explained, and this as well, and this as well. Okay, well, I didn't say this, but not all registers have rename registers. On some machines, for instance, the link register was not renamed. But the current Power CSLTH.SE, it has a rename register also for the link register. Okay, and some more things about the reorder buffer. So it's used to cancel instructions that should not be executed. And we realized that they should not be executed when a branch was mispredicted. Okay, and there are usually some very rarely executed instructions which are they are extremely rare, and they are maybe too complicated to exploit all this hardware. Then they are so-called serialized instructions, and what they can do is to implement them. All the older instructions can be required to leave the reorder buffer before such serialized instructions are allowed to execute. Okay, that's a trade-off between complexity of implementation and how to get still good performance for the common case. I mean, the instructions which are very frequent. Okay, so I hope you have understood two things from this lecture, namely pipelining for a 5-stage pipeline and superscalar processors. And this will become more clear when you see the execution of your int.opt in the IBM Power Simulator. So what you will do in that lab is to create a trace of instructions and feed that trace of instructions into this simulator, and then you will see exactly what happens in each clock cycle in the trace. So, and you can select an interesting function to start tracing. You don't want to start tracing from main. You want to start tracing when you come to a certain function. Okay.